Okay, here we go. All right, here we are, 10.2, day 2. All right, if you're looking here at this one, so you've done this warm up. So again, I want to find the 98% confidence interval for the true difference in proportions. You're doing a 2-sample Z interval for proportions. Random, yes, stated for both. Here's my checks. Again, I told you didn't have to necessarily show the numbers in between, but you can't just write this out and say it's greater than or equal to 10. Like, you've got to show me that you have these answers, okay? We know that the samples are independent of each other. These men and women are independent. We're going to assume at least 5,000 men and 21,000 women. Again, I didn't write assume because I kind of figured that has to be the case. The men are going to be my first sample. Here's the women. There's my sea level. There's my interval. 98% confident the interval from blank to blank captures the true difference in proportion of color blindness between men and women. Does the confidence interval contain 0? So no. So what could that imply? That the proportions are not the same. Okay? All right. Because I am not there today, we are going to skip this. And we are going to go straight to here. So when we are doing our significance tests for 2 samples, we have our null hypothesis is that P1, remember we're always looking at the difference in the proportions, so P1 minus P2 is equal to some hypothesized value. We're going to restrict ourselves to the easiest scenario in which the hypothesized difference is 0. So it's like saying P1 minus P2 is equal to 0, or P1 is just equal to P2. This is the way the calculator does it. This is the way your book writes it. I don't care which way you write it. I'm going to write it this way because that's how the calculator looks. Again, you don't have to have it equal to 0. That's just the easiest scenario. The alternative is that the difference is greater, the difference is less than, or the difference is not equal to, or again, you could write them like this. So this one right here, we're not actually going to carry out the whole test here. We're just going to write out the hypotheses. So they're looking at some laboratory gloves here and giving them some sort of stress. So 240 vinyl gloves, 63% leak viruses. 240 latex gloves, only 7%. So clearly there's a difference there. So test the claim that the vinyl gloves have a larger virus leak rate than the latex gloves. So like I said, I'm just going to write out the hypothesis here. I'm not going to carry out the whole test. We will do that later. All right, so you can use the 1s and 2s. Another way we could do it is we could always use symbols. So I could say like PV is the true leakage rate for vinyl gloves, and PL is the true leakage rate for latex gloves. Alright, so now with this here, you can, I'm totally fine if you use like the ditto marks. So basically that just means I'm repeating this right there. So I'm totally fine that you do that because I mean it's going to be the same thing, the true leakage rate for latex gloves. Alright, like I said, if you want to call these 1s and 2s, go for it. When you're writing it over here, whatever one you put first is going to be your number 1. So I want to test that the vinyl gloves have a larger leak rate than the latex. So I want to know if the vinyls are greater than the latex. Our null is just always going to be equal to. Alright, like I said, if you want to, go for it. You can write them out like this. Means the same thing, but your calculator's going to look like that. Alright, try the next one. Okay. All right, this next thing right here kind of goes back to, so here's your answer for this one. Again, you can write it either way. There's my ditto marks. All right. to get our test statistic. So the next thing here, you know that your test statistic is always the statistic minus the parameter divided by the standard deviation statistic. So we need to kind of remember a little bit from what we did before. And unfortunately for you, I didn't bring a textbook over with me when I'm recording it, so I'm going to grab one now. I am back. All right, so before, let's just look here at the one sample. So when we were doing our one sample procedures, this is in the back of your textbook. This is just in the, like the binding, like I just opened it up, the back cover, okay? So before, when we were doing our one sample procedures, so you can see here that we had, this was our formula for our one sample. This was our standard deviation formula. And if you remember when we did our test, when we found the standard deviation, we went back to the original formula from chapter 7, and we used the p, or in your book's calling it the p naught. But you can see here, this is p hat, this is p naught, okay? So the same thing kind of happens here. So in this chapter, we have two samples. So we talked yesterday about this one. So you're going to have your p hat 1, your p hat 1, p hat 2, and the n1 and n2. So just like up here with the one sample, we were using the hats. And just like here with the test, we were using the P. Remember when we did the test, we would always be like, so when we did our one sample test, you know, we would say like H, so naught would be P is equal to 0, you know, P is greater, I'm sorry, P is equal to 0.5, P is greater than 0.5. So when I found that denominator there, I was using that 0.5 in there. I wasn't using the p hat. So the problem here with our two sample procedures is that what we're doing at the start is we're not saying that we're equal to this one proportion. What we're saying in our null hypothesis is that the two proportions are equal to each other. So we want to kind of use that same idea here. So instead, again, confidence intervals using p hat, test just using p. So we want to use the same idea here where we're not going to use the p hats. We want to switch back to p, but we don't know what p is because we just said that they were equal to each other. So since we're saying that they're equal to each other, what we do is we do something called a pooled proportion. So we put them together. So we take the successes from each sample, add them up, and then divide it by the total sample size. And we call that the p hat c. That's what we're using here in this formula. So instead of using p hat 1, the only reason why this is different from the confidence interval is because in that null hypothesis we make a statement about what we think is true about the proportions. So if we think they're equal, we should put them together and create one proportion. So that, again, that's that formula that I just showed you in the book. And again, that pooled sample proportion is if we think that the null hypothesis is true. So if P1 equal to P2 is true, then we should just combine the two proportions and put them together to make one. So I have, using the above example here, that P hat C. So I had 290 in my first sample and 50 were injured. I had 123 in my second sample and 16 were injured. So I'm putting those together, and that's my p hat c. And that's what I use in this denominator. I'm going to do a problem using the formula and using the calculator so you can see where that p hat c is coming into play. Alright, so just like before, so we've got our state plan due. So we know that, you know, we just talked about the HO and the HAs. We're doing a two-sample z-test for proportions. You can say for difference in proportions if that makes you feel better. I won't require it. Is the data collected randomly or is it from an experiment that was conducted randomly? So you got to check both samples here. Is the sampling distribution normal? All right, I need to reference this chart again. All right, if we think back here, back here in chapter when we were doing one sample procedures. If you notice here, when we were doing the confidence interval, we did n times p hat greater than or equal to 10 and n times 1 minus p hat greater than or equal to 10. But when we did the test, we did n times p naught. So again, whatever we had in that HO, that's what we used in the check. So if you don't believe me, just go back, look at your notes. All right, so here we made a switch. We had a slightly different condition based on what we were doing. Well, your book says, we'll just make your life easy and make the checks the same here. All the AP rubrics realized that these checks are different and these checks are the same. The more correct check here would be to use that p hat c. So you would have like n1 times p hat c to see if that was greater than or equal to 10. You would check n1 times 1 minus p hat c to see if that was greater than or equal to 10. And then you would do the same thing for the 2's. But like I said, that requires that extra step of calculating that p hat c. And like I said, your book says it's okay, we'll let you get by here on this one, and we'll just make these two checks the same. All right. You're independent. So again, just like yesterday, samples independent of each other. Are the observations within a sample from an experiment with random assignment? Then if that's the case, we're good to go. If the observations are from a sample taken without replacement, then you have to check that 10% condition. You want to check both samples. All right, if your conditions are met, then you perform your calculations, show your work. Again, this is that denominator. So remember, it's the statistic. In this case, the statistic is the difference in these minus the parameter. So the parameter is really this P1 minus P2, but we said in the null hypothesis that we said earlier that we were always going to deal with the easiest scenario in which this is equal to 0, so that's why I just have 0 there. Here's the calculator command. If you were doing it by hand, you'd find your p-value using the normal CDF, because we're still following that standard normal curve, that z distribution. This right here looks the same. This little footnote down here is about that check that I just went over with you when I looked at the back of the book. Okay? All right, let's talk about teenagers going deaf. So are teenagers going deaf? All right, so we've got a study here of 3,000 randomly selected teenagers in this year, and 15% showed some hearing loss. In a similar study of 1,800 randomly selected teenagers, 19.5% showed some hearing loss. So does these data, or do these data, however you want to say it, give convincing evidence that the proportion of all teens with hearing loss has increased? So I am going to make P1 the true proportion of teens with hearing loss in 1988 to 1994. And I'm going to make P2 the true proportion of teens with hearing loss in 2005 to 2006. So my HO is going to be that the two are equal. Again, if you want to write out like the subscript, you want to make that 88, like if you want to use the years, so 88 to 94, 05 to 06, that's fine. You still have to define the terms here though. You're not getting around that. All right, we want to show if the hearing loss has increased. Okay. All right, so I'm doing a 2-sample z-test for proportions. Again, if you want to say difference in proportions, that's fine. Random. So yes, stated for both. All right, the normal. So like I said, the book said, okay, we'll make your life easy. So you just need to do like n1 times p hat 1. So we have 3,000 times 0.15, and you know, n1 times 1 minus p hat 1. So that would be 2,500, because these two together have to make up 3,000. 1,800 times 1.95 equals 351. This one over here is I can't read my 1449. All of them are at least 10, so that tells me my sampling distribution is approximately normal. The independent check. The samples are independent of each other. I know they're independent of each other. If you were a teenager in 1988 to 94, you're not still a teenager in 2005, 2006. And then within the sample, I need these people to be independent. So I got to assume at least 30,000 and 30,000, sorry, and 18,000 teens in the respective years. All right, so again, like I said, if I were going to use the formula, here's the problem. I have to calculate that p hat c to use the formula. So if I'm using the formula, that p hat c, so I'm going to take this. So again, it says so the p hat c is x1. So obviously we know the sample sizes here, the 3,000 and the 1,800. All right, to get that x1, again, so if I just have my 3,000 times my 0.15, that's 450. So I had 450 successes in the first sample. If I do my 351 would be the number, because that was the 1,800 times the 1.95. So I have 351 in the next sample. So then I'm going to add these two together, divide by my total. So this is my p hat c. So if I were doing the formula, I would have to do the point, so my P1 is my 15% here, so I would have to do my 0.15 minus my 0.195 divided by, and again this is Z. So I would do the, this P hat C, so I don't know, 1.669 I'll do, minus 1.669 over 3,000 plus, again we have that 1.669 times 1 minus 0.1669. Remember, it's that p hat c, we're putting them together, over the 1,800. So I'd get that answer, okay? Just don't forget this formula. You don't have to remember. You should be able to recognize the formula if you see it. Alright, I could solve all that, but we've already discussed how it's going to be time consuming, and there's definitely opportunity for errors here. So my better approach is to probably just try to use the calculator. So I go to stat tests. I go to 2-prop z-test. So I'm going to have my 450, my 3,000, my 351, my 1,800. All right, what is the direction of my HA? So my HA says that P1 is less than P2. So I'm going over here. I hit calculate. Okay, so you would tell me what your inputs are. Tell me what your test statistic is. Tell me what your p-value is. Look, it's times, it's a very small number there. Do you see how the calculator, so the calculator gave me back the p hat 1, it gave me back the p hat 2, it gave me back the p hat. That p hat is your p hat c, so that's just what I calculated right there. So the calculator calculates that because it's using that when it finds that test statistic for you, right? So this test statistic is pretty far away from the mean, right? That's giving us a small p-value. So the p-value, I had a significance level of 0.01 in the beginning, was less than alpha. Again, you could compare it if you want. So 2.58 times 10 to the negative fifth is less than 0.01. So if it's less than, I reject HO. There is enough evidence to support the proportion of teens with hearing loss has increased. Okay? All right. Try the one on the last page. You know the drill. It's hard to see some of this because I copied it. Here's the answer. So again, it's the true proportion who would quit smoking in the financial reward groups. Then without rewards, again, you can switch those. I picked a significance level. There's my method. There's my random. Here's my normal check. Okay. So the random assignment, each groups are randomly assigned. So this problem right here, I am not talking about taking a sample from a larger group. Like in the last example, I was taking a sample of teenagers from a larger group of teenagers. So I was kind of messing up that idea of independence. I'm not so much worried about it here because here I'm just referencing the volunteers. So when I do that random assignment, basically just pay attention to if your problem is referencing a random selection or if it's referencing random assignment. In this case, because I'm referencing random assignment, the random assignment is going to make the groups independent of each other. And then I also, within the group, I'm going to assume that people's decisions to quit is independent of each other. I go through the whole problem. I get a pretty small p-value. It's less than alpha, so I can reject. There's enough evidence to conclude that a financial incentive helps people quit smoking. Okay, so that's that for this one.